Yes! Welcome back. Well, today we're gonna create something that no one has ever made before. We will build a working replica, one of the iconic mnemonic displays from the Chernobyl reactor control room. And we will do it in such a way that any of you can follow and build your own. So, let's do it. In one of our recent videos, we took a close look at what these displays are. If you haven't seen it yet, here's the core idea. So, they show a simplified layout of all the main systems of the reactor unit. Here you can see operation of valves, pumps, turbines and many other things, and they also display important warnings. We will focus on this panel because it shows a few standalone systems. These are the integrity of the reactor's active zone, cooling of the control rod channels, cooling of the side biological shield and the status of the spent fuel pools. But at an operating power plant, most of this is constantly glowing, blinking and changing. But how exactly it happens and what each element means we'll get to a bit later, when we'll power our display up. And first step, we need to choose the right technology. So, originating from the 70s, these panels were based on the electroluminescent principle. Each one is basically a sheet of glass layered with conductive and insulating materials in specific shapes. So, when electric current is applied, certain parts glow across their surface. On the back, everything is sealed with a thick layer of epoxy resin, from which many wires emerge. It sounds solid, but these panels actually had a few serious drawbacks, so they required 400 volts AC and ran quite hot during their operation. So as they aged, internal short circuits sometimes developed and in several cases they literally caught fire. And so instead we'll use another technique. So in fact most of the RBMK controls are based on light bulbs projecting their light to various masks with inscriptions. But instead of those we'll use RGB LEDs mounted on a solid non-transparent plastic panel. Next we'll add 3D printed light separators. Then a semi-transparent white acrylic sheet on top and finally a non-transparent mask that matches the diagram. We'll secure everything with metal frames and mount it on a large metal panel. The best choice is 5V addressable LED strips. An addressable LED has a chip inside, so it can be controlled individually. They come in chains of 50, which you can cut or extend as needed, so I picked extra connectors for that. A rough estimation is that we will need around 13 strips, for a total of around 650 LEDs. At full brightness, that setup would need around 40 amps, so we got a suitable power supply. Well, honestly, that's more a precaution as we'll run them at about 60% brightness, but still it's important to distribute the power evenly, so each strip will have an extra power connection point. That said, we started, so first I opened a Dub Illustrator and redrew the panels, matching the size and proportions of the original elements. The larger panels at 30 by 30 cm and the smaller ones at 30 by 20. I used one of the standard Soviet engineering fonts for the notations. Then I created two sets of images, one for printing the back panels and one for the masks. The masks are mirrored and inverted, because just like the originals they are applied from behind. Well, it took weeks to find the proper technology, but eventually we went for ordering ultraviolet printing on acrylic, and a few days later we got these parts. For now they have a little bit strange color because there is a protective film we'll remove later. The printing company suggested an effective way to achieve this full non-transparency, so first they applied the grey color we will see from the front, then a layer of white and finally 2 layers of black, and the result looks just perfect. After that we received the laser-cut semi-transparent filters. Well, this material is quite sensitive, so it burned out a bit on edges, but that's really not a problem because these marks will be completely covered. And finally, here are the back panels, where we will drill openings for the LEDs. Well, of course we could laser cut them as well, but in reality it turned out to be more convenient to make them manually. Just like in the original panels, everything will be secured with metal frames, and as you can see they have this hammer textured surface. So we decided to use 15mm U-shaped aluminum profile which we cut into segments. But hammer paint doesn't hold well on bare aluminum, so first we applied a sprayable acrylic primer. This is the surface we need. Then we applied grey hammer paint and let the segments rest for a few days so the layer and texture could form properly. This is what we got. Next, we designed the separators, so I traced an outline over the image to define the required positions. Then, based on this, we made 3D models. We decided to use a low-end printer to test if it is sufficient, and a few days later we had a lot of parts printed. Since the panels are larger than the printer's work area, we will need to glue the segments together in a few places. Then we additionally reinforced the connections with the thick adhesive tape. In a similar way, we positioned the back panel and drilled openings to secure it with screws. Well, at this stage I discovered that the outer border was a 1/4 millimeter too thick, so I had to cut off a thin layer of plastic to make it fit into the metal frame. Well, although I opened the internal grid, the parts didn't lose their strength. The next step is to make openings for the LEDs. Of course, we could pre-cut them using a laser, or even make a back panel and separators as a single 3D printed part. And honestly, now I'm sure that would have been ideal. But at the time of printing, we didn't yet know what exact size and type of LEDs we'll use, because they actually come in different shapes and sizes. And since this is essentially an optical device, it's quite important to remove any plastic debris or dust, so keep a vacuum cleaner somewhere nearby. And after we made all that, this is what we got. Before proceeding, we needed to make the metal chassis, so we made this sketch and sent it to our friend Dmitro, who is well known for solving the impossible in a short time. To stay close to the original, the chassis is built from 2mm steel, and on the back there is a simple but yet durable support frame made from rectangular pipe, welded at a few points. Unsurprisingly, that same evening he sent us the video of the already finished job, with a small notice that it was already shipped. So next day, once it arrived, we brought it for sanding and powder coating, and in a couple of days later, the panel was ready. Well, the surface turned out perfect and the color matched the original really closely. Maybe the welding isn't the cleanest, but I think it will do the job. And then, after checking that everything fit perfectly into the chassis, we began positioning the LEDs. They fit tightly into the openings, but I think it's better to secure them with the hot glue. Where LEDs are too close together, you might need to remove the silicone shield. Well, that's not a problem, because LEDs are already sealed in epoxy resin. Speaking of placement order, there are 2 ways to do it, so you can plan everything in advance, make a map and just follow it. Or you can place them randomly and then map their position by lighting up, say, 10 at a time in different colors. We went for the second option and surprisingly it took less time. Each module has a different number of LEDs, so the chains had to be cut and fitted with connectors, and here it's very important to pay attention to polarity. Then, to each LED chain we added extra power and ground lines. This is very important, because the total length is quite large, and without it, voltage would gradually drop, affecting performance and brightness. And once all this was done, we moved to the front part, and here came a big challenge. So, in the original displays, inactive elements have this brownish coffee with milk color, but when they glow they appear emerald green. Printing a thin brown layer on the mask wasn't really an option, because ultraviolet print has a visible grainy texture. Adhesive film didn't work either, because it was too thick, and after many experiments we found an elegant solution. So we took an extremely thin matte film, used for decorating flower compositions, so it shifts the light color just slightly, just enough to achieve the desired effect. First, we removed the protective film from light filters. Well, they have a glossy and matte side, and this matte side must face the light source. We needed 2 layers of this film for each module, and since it's very thin, the easiest way to cut it was to place the film on a pizza box, position a white filter on the top, and just cut around with a sharp box cutter. And once pieces were ready, we secured both layers with small pieces of adhesive tape. Well, you need to maintain even tension and be careful not to bend or wrinkle the film. Then we once more cleaned the mask, removed its protective layer and carefully positioned it, again using adhesive tape to hold it in place. And finally, we assembled everything together and secured it with the frame. Well, I do not recommend applying glue at this stage, it's best to leave room for some micro adjustments. And that said, we powered everything for the first test. I covered the front with plastic film because Fuzik already came to inspect it and left a few cations of fur. So what I discovered, a few areas had irregular glow, that's probably due to minor 3D printing flaws, and I also realized that each pump should probably have 2 LEDs instead of 1. Also, 1 LED turned out faulty and will need to be replaced. Once I corrected everything what I could, I applied a layer of glue from the back to secure the frame. And next it was time to assemble everything together. And so I placed the metal panel upside down, resting it on 2 stacks of magazines, and began carefully lowering the modules into place. Well, using magazines might sound like a strange solution, but in fact it allows to gradually lower it down without damaging the wiring, because the whole metal panel weighs nearly 20 kilograms or about 45 pounds. So as you can imagine, one wrong move and it will just ruin everything. And this is what we got. As a tiny historical side note, so this backside view doesn't look too different from what is actually behind the wall in the control room. Once out of curiosity I checked what remained at the control room floor, so there is still much of the original structure, and it is visible it was connected with countless wires, pretty much like what we have. Then I secured each module with 4 aluminum strips. Well, while the backplanes held up fine, I eventually came to conclusion that 2mm plastic was somewhat a bit too thin, because it's deformed slightly in few places. And finally we needed a rear cover to protect all this wiring. At first I tried to find a sturdy plastic tray, like those used in supermarkets or shipping companies. That actually would be an easy and effective solution, because it would cover everything at once, but it appeared none had the right inner dimensions. So eventually I got 6 thick plastic forms used for casting pavement tiles. They matched the size of each module just perfectly, and they also had 90 degrees walls. We bolted them together, attached L-shaped mounts, and placed this entire structure over the frame, and as you can see it fits exactly into the size and railings, and all what remained was just to secure it. Perfect. The bottom section is reserved for the power supply and controller. Well, for now I don't have a proper panel, so I just mounted them temporarily on the plastic bottom of an old keyboard. Fast forward, after more than 1 hour of operation, the power supply stays just slightly warm, so this temporary solution actually works. And this is what we have built. To my mind it looks pretty close to the original, but now let's test it. We will explain the programming and wiring in all detail in the project documentation, but basically you can add buttons, switches and make it completely interactive. But for now I have written a simple program to cycle through several operation modes using a single button. And so the first mode is an indication test, where all LEDs light up at once. The second mode simulates normal operation, so here let me explain what we are seeing. This large rectangle shows the active zone of the reactor seen from the side, and the diagram represents the independent cooling circuit for the control rod channels. Here is the tank for this water, which has also 2 warnings for levels inside. This type of warnings always marked with horizontal lines and the letter H for height. There are also 2 numeric notations, so the operator can read exact values from the Scala computer, but now everything is off, which means everything is just fine. Next, the water flows to these 4 pumps, and each is equipped with a device to remove excess hydrogen. They are needed because radiation can split some small amount of water to oxygen and hydrogen, and any gas buildup in this tank is really not good. Then, above 4 valves, and glowing ones are opened and dark are closed. Then, 2 of the pumps are running. This one is in so-called automatic reserve. It is not running itself, but its valve is open, and the pump will start if it will be needed. The 4th one is currently offline, but why here is the separator symbol? That shows it has dual power supplies. Alright, so now let's simulate a change. The 1st and 2nd pump go offline and their valves close. The 3rd and 4th will start, and half of the 4th glows less bright, which means the backup power supply is ready but not currently engaged. These warnings here are G for consumption, P for pressure, and T for temperature. These letters mean exactly that, wherever you see them on these diagrams. From the collector, the water moves into this receiver tank. Well, you remember the level warning, but here the line is above the label, which meaning it is for high-level alert. This little Pac-Man shape is a rotometer, it measures the flow, and it also has a warning as does the pressure. Then the water enters the cooling rod channels, and if they overheat, the warning next to them will activate. At this stage the water becomes hot, so now it needs cooling before it can circulate again, and this happens in these 3 heat exchangers. One is dark because it's offline in reserve and 2 are active. The exchangers are cooled by technical water from the cooling pond, which is delivered by these 3 pumps. There can be 1 or 2 pumps active, but one is always in reserve. Below that is a separate system. These are indicators for the spent fuel pools next to the reactor. So, when fuel rods are removed, they are still very hot, so they are stored underwater in these pools. And so, these are critical warnings for rising temperature and dropping water level in pool number 1 and pool number 2. This smaller section shows water supply to the L scheme. That's such a large tank surrounding the reactor which acts as its side biological shield. I guess now you can read it. So this is intake, then there is a receiver tank, 2 pumps and 2 valves. One pump is active and another is in automatic reserve. So let's switch them and add a short warning for the level inside the receiver tank. That's what it looks like. Now let's look at the upper part. So these are large structural reactor elements, so-called schemes S, OR, KG, E and G. Each has own temperature warning. Then around here are warning indicators for concrete, graphite and panels temperature status. But there is no scheme L here, because its warning is below. This round diagram shows the reactor core from the top. In normal operation, very little lights up, and if more does, then something is pretty much wrong. The outer ring signals overheating of the neutron reflector. It is split in 4 segments, each for 1 reactor quadrant. And what are these triangles inside? Well, that actually is quite interesting, but I need to give a little explanation. So, the reactor core holds over 2000 channels inside graphite columns. During operation, channels and so graphite heat up, and to cool graphite, a gas mix of nitrogen and helium is constantly pumped through. But in addition, that is also used to indirectly detect problems. So if we imagine that some channel suddenly ruptures, local temperature also will rise. Each individual channel has a sensor, and they are linked to 26 group valves, which are shown here with these pictograms. If everything is fine, only the left triangles glow, showing normal gas flow. But if a group valve detects trouble, a number of it appears. The operator can then trigger increased suction to cool this place down. And when they do this, the bottom triangle lights up and the right one starts to blink. Once the switch process completes, it glows steady, and simultaneously the message in the upper right corner switches from normal suction to increased suction. Then, when a valve hits its set point, a rectangle glows, and soon everything returns to normal. This block of indicators shows the gas supply status, with overpressure warnings and diamond indicators for pressure anomalies. And these arrows indicate venting of excess steam gas mixture. Finally, at the bottom, there is one last warning saying Air of KGO. KGO stands for the Fuel Rod Integrity Monitoring System. The thing is, in fuel rods uranium is sealed in zirconium tubes, but there is no way to see them during reactor operation, so any problems are also detected in indirect way. If a seal of a tube fails, radioactive byproducts enter the coolant and travel by pipes. And under the drum separators there are 4 unmanned holes. They are moving special automated cards that constantly scan coolant pipes for abnormal radiation. They detect a specific pipe, and given that each pipe corresponds to its own channel, based on this a faulty rod can be easily identified. However, these holes run at about 300 degrees Celsius or 570 Fahrenheit, so if it gets too hot in there, the warning activates here. So that was the basic operation of these displays. We could make all that thanks to the incredible help of our consultants, people who back in the day worked with this very type of equipment. But besides, for us it felt really special to bring it back to life 25 years since the reactors were shut down. And for those who want to build the same, we have put all the project documentation, instructions and files in one free post on our Patreon page. It's absolutely free to access, but this way you will be able to get constant updates, because what you saw today is just one milestone. If you would like us to build a matching operator's control panel for all these valves and pumps, just let us know in the comments. And in the meantime, get ready for the next Chernobyl replica we are already building. So subscribe for more, and we'll see you in the next one.